So for this first one, as we can see, hello, good morning. This is the Lewis dot diagram of sulfur trioxide. Now, let me start back at phase one, only because I would really like to revisit Lewis dot diagrams. It's been a while, like a long while. I had a nice list of rules for you way back in the day. And I would strongly recommend that sometime in the next week, you go find those rules for Lewis dot diagrams and revisit them. I'm going to verbalize them right now, but knowing how to do a Lewis diagram on the test is probably a good thing. And by probably a good thing, I mean it's a really good thing to know how to do. They're going to ask you. There is a very, very good chance you get something similar on the test next Friday. So let's revisit how to do this, okay? First thing you want to do when trying to draw out a Lewis diagram is total valence electrons. How many electrons do I have to work with? So valence electrons are based off of the column. First column, 1. Second column, 2, so on and so forth. You skip the transition metals, but the boron family has 3 valence electrons, the carbon family has 4 valence electrons, the nitrogen family has 5, oxygen family 6, halogens, fluorine, chlorine, bromine, iodine, have 7, and then the noble gases we're never really going to use, right? So I've got oxygen, 3 of them, valence electrons are 6, for a total of 18, plus sulfur, which also has 6. So I've got a grand total. Did it work? Whoever drew on there, did it work for you?
Yeah, they mixed.
Is this the joke?
Yeah.
Excellent. Give me a sec. Trying to help you. I have 24 electrons to work with. Now, if it's a molecule, spoiler alert, we need some bonds. We're going to start there. Okay. The very next rule says, let me make at least one bond between all of the whatevers I've got. So that requires 2 electrons per bond. Okay. Every bond contains 2 electrons. So I've used 6. That leaves me with 18. I then add electrons around the outer atoms first, up to the octet rule. So currently, each of my oxygens has 2 electrons around it. They each have just the 1 bond. And I can add the remaining 18 of these around the outside. Now, at this point, all of my electrons are on the structure, but it's not great for a couple of reasons. Generally speaking, the octet rule is your friend. Okay, if you remember the octet rule, that's the rule that says, like, most of the time, atoms and elements want 8 electrons around the outside. Okay, so the oxygens are all happy with the octet rule. I've got 2, 4, 6, 8, 2, 4, 6, 8, 2, 4, 6, 8. But the sulfur, as the way it's currently written or drawn, has 6. So at the very least, we would want to get sulfur up to 8. Okay? And in reality, AP will actually accept this as an answer, which is kind of wild in my opinion. I think they really shouldn't, but they will. You've added all of the electrons appropriately, and the octet rule is satisfied for all 4 atoms. This is a potential correct answer, but there's way more. 1, because if I left it like this, there's also something called resonance, right? Resonance occurs when it's like, I have an equivalent place to put a bond. For example, I need a double bond according to the octet rule, but does that have to be here? What about there? What about here? What's the difference between those 3 locations? Nothing. So where I decide to put that is irrelevant. Okay? But here's the other thing. We also have formal charge. Okay? I taught you how to do formal charge. That is a better metric of molecular stability. So let's go there. The formal charge equation is the number of valence electrons minus dots and dashes. Okay, minus total dots plus dashes. You can do this little calculation for every individual element. And the idea here is that formal charge, when it's 0, represents the best possible arrangement of electrons. So, if I check the formal charge, currently this oxygen with the double bond would have a formal charge of 0. Okay, I would have 6 valence electrons originally on the oxygen minus 1, 2, 3, 4, 5, 6 dots and dashes. So this formal charge, equals 0. That's good. The formal charge over here equals 6 valence electrons minus 1, 2, 3, 4, 5, 6, 7 dots and dashes. Minus 1. Minus 1. Same calculation, right? The formal charge is negative 1. Formal charge is negative 1. What would the formal charge of sulfur be? Positive 2. Can we do better than that? We sure can. So if we keep going and make more double bonds, we're going to make this a better structure according to formal charge. We're going to break the octet rule on sulfur, but if you remember, that's kind of allowed sometimes.
Second row.
Correct. It needs to be on the 3rd row of the periodic table or lower. And the reason why is it needs to be big enough to handle that many electrons nearby. If atoms are too small, they cannot accommodate 6 bonds or again, 12 electrons, right? Because if we make this fully double bonded all the way through, sulfur has 12 electrons around it. That's a lot. And it's okay if it's big enough to handle that. Small elements like the ones from row 2 cannot. You cannot expand the octet rule of an oxygen or a nitrogen, for example. They are stuck. 8 is the max. But if we're beyond that, they generally allow it, and they're generally able to accommodate. So, very long-winded, I apologize. We'll speed this up in a second. But long story short, I can fix formal charge and make this better. So I'm going to do that. Okay. And if I go like this, sorry, my lone pairs are kind of wonky, but I think this is the best possible structure. Okay? AP accepts anything as long as all the electrons are correct and at least the octet rule is satisfied. They would accept this structure with 1 double bond. They would accept this structure with 2 double bonds. They would accept this structure with 3 double bonds. But again, you need 24 electrons on the structure, and at a minimum, octet rule must be satisfied everywhere. And the way you do that is at least having 1 double bond. Cool? Dylan.
If we were to draw like the first way, would we have to draw all the residence diagrams?
Oh, no. One appropriate structure is plenty.
Okay.
Yes, unless they specifically ask for resonance, oh my gosh, please don't waste your time. Yep. And I don't think they ever would.
Okay. I'll trust you on that.
Okay, Dylan.
Predict the shape of the SO3 molecule based on the diagram you completed above. Another good review, because I had lots of questions on this too, right? Molecular geometry. It is off of the coordination number. There is a theory called VSEPR theory, VSEPR, valence shell electron pair repulsion. The theory of molecular structure is that when I have electrons around my central atom, those will try to separate and repel one another to get as far away from each other as they can, right? So in this instance, I have a sulfur in the middle. And around my sulfur, I have 3 oxygen atoms that I'm really trying to separate in 3-dimensional space. So these will repel and push one another until they are as far away as they can possibly mathematically get. The results of a coordination number of 3, like this is, give us a trigonal planar shape. You probably want to go back and check your shapes just a smidge before next Friday. Really, really focus in on tetrahedral. Coordination number 4, that's generally where they hang out. Okay, if you're going to get a molecular geometry question, it's probably a tetrahedral shape, and they might ask you the bond angle. If you've done enough practice test stuff, you've probably come across a problem that's like, what's the bond angle in this thingy dingy? And it's generally tetrahedral. What's the angle of a tetrahedral? 109.5, 109.5. Okay, you're probably going to be asked to provide that angle next Friday. I don't know the context. I don't know the molecule. But generally speaking, when they start talking about geometry and they start talking about angles, they're probably giving you tetrahedral. Sometimes they give you trigonal planar. But they generally don't get crazy on you. They're not going to ask you to like figure out that you have a seesaw shape. Okay? If you remember what that entailed. Coordination number 5 with 4 atoms and 1 lone pair. That stuff was fun. That's good stuff.
Yeah.
Well, we're not doing proofs.
I
That's not fun.
Feels like chemistry is one giant proof.
Kind of.
Like this is
That's
how
science,
this works.
isn't it?
Here's
Yeah,
why
that's
it works.
So again, please, you need to know how to do Lewis diagrams. I think this was a good little review. You need to know how coordination number works. Speaking of coordination number, let's talk about another thing with it, just while we're here, because this is more than just doing this stuff, right? Coordination number and hybridization. I've answered like 2 or 3 questions about that already this morning. Coordination number with hybridization. All you need to know about hybridization is how to identify it. It's not how it happens. It's not why it happens. It's not how it visually looks. Hybridization, all they're ever going to ask you is like, what is the hybridization of this? Or like the one we kind of answered earlier with a couple of you guys. Hybridization was this. What is it now, right? So identifying hybridization of the orbitals is 100% based off of the coordination number. If you have 4 things, a coordination number of 4, that is sp3 hybridized. If you have a coordination number of 3, it's sp2 hybridized. If you have a coordination number of 2, it's sp hybridized. There's a little table in one of those note sheets in that unit that literally just has that information. You just kind of need to memorize that. If you understand 4 things separated equals sp3, 3 things separated equals sp2, 2 things separated equals sp, you're good. And it's going to get asked. There'll be at least 1 question on it, but probably just 1. All right. Under some conditions, SO3 decomposes to produce SO2 and O2, as represented by the equation below. Under what temperature conditions will the reaction be thermodynamically favored? High temperatures, low temperatures, all temperatures, or no temperatures? Justify your answer in terms of the change in enthalpy and the change in entropy during the reaction. It's like what we're doing now. This should maybe be like, not bad. What we need is our handy dandy equation. This is what we need. This is everything we need. Okay? Let's think about what we have and what's going to make this process thermodynamically favorable, right? When it comes to this expression, the end goal is Gibbs. If I want it to be thermodynamically favorable, what should my Gibbs equal? A negative value. So the end goal is I want this negative. Okay, how can I achieve that? Well, I can achieve that a couple different ways. I have 2 terms. I have an enthalpy term and I have an entropy term. My entropy term also includes temp, but don't forget we're using Kelvin. Kelvin can never be negative. It's the absolute scale of temperature, meaning it starts at 0 and it goes up. Okay? So when this term is negative and this term ends up being negative, it is quite literally impossible for me to not have a thermodynamically favorable process, right? Mathematically, this is a math exercise, more or less. If I make this thing negative and this product over here is a negative number, well, sorry, negative after I include that, right? Negative here, spoiler alert, it's always thermodynamically favorable. Let's give you the opposite of that, right? If this is positive, and this ends up being positive after I account for that, it's impossible for me to make it thermodynamically favorable. So that's the options they're talking about, right? All temperatures, no temperatures. Do the numbers work out where it's impossible for me to make it thermodynamically favorable? Do the numbers work out where it's impossible for me to make it thermodynamically unfavorable? Or do we have one of these weird hybrid situations where we actually need to consider the temperature? Let's look at my options. What they've given me so far is the enthalpy. They're telling me that I have a positive term. Did they give me entropy? Well, they didn't directly give it to me, yes? But can we contemplate what would happen to the disorder of this process? Yeah, we can. I'm going from 2 moles of gas to 3 moles of gas. Sounds like an increase in entropy to me, right? So they literally want you to make a prediction on delta S in this one. So we're predicting that this is also positive. I think that makes sense. I think it's pretty obvious, actually. I feel very, very confident in that prediction. So we're under a situation right now where this is positive, this is positive. What does that do to this term, though? If I have a positive entropy, this term overall will be negative, which is a good thing, right? We want the delta G to be negative. So these are competing. I have a positive enthalpy competing with a negative T delta S. Which one do I want to win? The T delta S term. That's ideal, because then if this is bigger than this, well, then I got my negative Gibbs like I want. So how can I make this bigger? Crank up the temp. I can't change the enthalpy, is what it is. I can't change the entropy. I don't know what it is, but I do know it's positive. But those values are inherent to the process. So what can I change? The temperature.
So you have to get rid of below degree symbol then?
Yeah, so then I'd be under non-standard conditions. Don't worry too much about that, but you're right. But if I increase temp higher and higher and higher and higher and higher, and I make this term bigger and bigger and bigger and bigger, eventually I hit a spot where this term is larger than that term. And when that occurs, I get my negative delta G just like I want. So let's phrase this all out. Under blah, 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 blah. Okay. The reaction will be thermodynamically favorable. Sorry. Those are big words.
I feel it.
Under high temperatures. Okay, I'm going to be a little lazier today. I've been talking a lot. I want to get through this, is what I'm saying. That's my answer. Now I need to justify, right? The justification is that the enthalpy is positive. And the, how do I want to say this? T delta S term will be negative. As a result, as temperature increases, Gibbs free energy will become more negative, making the process more thermodynamically favorable. I don't know if that's a perfect answer by any means, but again, I'm trying to explain all angles of what we got going on, right? Yes?
Would it be all right if we just justified saying the change in enthalpy and entropy are both positive? Or Or do we have to like clarify the?
I don't know if that's enough.
Okay.
Yeah, I don't know if that's quite enough. Let's see what they have. Let's read their answer. What do you got, AP? Reaction will only be thermodynamically favored at high temperatures. Okay, great. The reaction will be thermodynamically favored when delta G is negative. Delta H for the reaction is positive, so at low temperatures, when the value of T delta S is small, delta G is positive and the reaction is not thermodynamically favored. Because delta S for this reaction is positive, high temperature conditions give a large positive value for T delta S. This will result in a negative delta G and the reaction will be thermodynamically favored. I think that, yeah, so they do want, it sounds like they want an acknowledgement of Gibbs being negative as the end goal.
So that would, we have to talk about G.
It's on the right track, it's just not enough, I don't think.
You have to talk about G.
Yes, so from my interpretation of what they provided, you need to acknowledge that the negative Gibbs is the end goal.
What's the point? Do they have like a point?
Yeah, I mean, the point is for, did you say this?
Okay.
And then the next point is, 1 point is earned for assigning the correct sign to delta S and linking it to the favorability at high temperatures.
How many points is the question?
2.
So
1 for the right answer, 1 for the justification. And that's how they always worked it, by the way, right?
Even if you guess, I think it's guess high temperatures.
Yeah, you get a point. Yep, you get a point. Sometimes the point is tied to the justification, meaning like sometimes these are 1-pointers,
Yeah.
and you don't get it without the justification. But sometimes it's also it's like this, where it's a 2-pointer.
Do you have to specifically state changing enthalpy, or can you just use the symbol?
They'd probably be fine with it. They'd probably be fine with it. I mean, don't get crazy shorthand. I went way too much shorthand right here, right? I think I would, on the real test, I would write that out. On the real test, I would write that out. On the real test, I would write that out. But I think you're fine doing that. I think you're fine doing that.
Sorry, I'm just kidding.
Again, I'm trying to cut a corner or two to make sure we're staying on time here. Make sense? Make sense?
Yeah.
So this relationship of this equation will show up. I don't know how they're going to use it, but they will make you contemplate whether Gibbs is positive or negative. Sometimes, and again, if you've done enough of the practice test, you've come across this by now. I can almost guarantee it. There'll be a question where it's like, here's your enthalpy, here's your entropy. Is this going to happen? And it's a matter of kind of just plugging and chugging and understanding the relationship. If delta H is negative and delta S is positive, mathematically speaking, I can't get anything except a negative Gibbs. So there's situations where it's impossible to get anything other than one outcome. Then there's other situations where if they're both positive or if they're both negative, temperature is a big deal or is dependent upon what's going to be the outcome. All right. Chemist fills a rigid vessel with sulfur trioxide at a certain temperature until the pressure of SO3 in the container is 0.83 atmospheres. The SO3 decomposes as the partial pressures of SO3 and SO2 and O2 in the container are monitored over time, as shown in the graph below. Changes made to the system at time T1. Okay, cool. Answer the following based on the graph. Draw an X on the time axis to show when the system first reached equilibrium. All right, definition of equilibrium. What is equilibrium, right?
Right, and first part is the first part.
Correct. The forward rate and the reverse rate are the same. And what would occur when the forward rate and the reverse rate are the exact same? Huh?
Flatline.
So this is molarity or partial, I guess not molarity, but partial pressure of gases. And as time progresses, right, we had the initial SO3, and then it's breaking apart, it's breaking apart, it's breaking apart. As it breaks apart, we're producing these two products. And at a certain point, we level off. When we level off, that means the molarities or the partial pressures or the concentrations are no longer changing. That's equilibrium, right? Now, are things still happening? Yes, equilibrium is dynamic, right? Reactions are still occurring. It's just that when I break apart the SO3, I am equally as fast breaking apart these two things to produce more SO3. Both reactions, both directions, I don't have the reaction on this page, but both directions are occurring at equal rates. And that's represented by the fact that our molarities are no longer changing. So where would I put my X? Right there. And And they set on the axis, so I'm gonna put it where they want it, right? If I put it like up here, they'll probably give me credit, but let me make sure I read the instructions.
What's that like? To the right of that?
That little guy?
Like all of them.
I wouldn't worry about that one. Describe the change that was made to the system at time t1. Okay. So here's time t1. Let's analyze what they just did. We had reached equilibrium, and we let it sit for a good little chunk of time. And then all of a sudden, it's like, boom, something happened. What happened based off of your interpretation of this spot?
They added SO2.
They added SO2. That big spike in molarity of SO2 is basically representing the addition of this substance. Now, as a result of that addition, what happened to the other two things? Well, they responded, right? This is the stress. This is the shift. So, with that in mind, let's just answer the question. This was a straightforward one. What was this change that happened? Well, I think some SO2 gas was added, right? I think that's all we need. There's no justification point here. There's no weird, whatever. What do they have? I'm just curious. Additional SO2 was injected into the reaction vessel. What a
Why
nice.
did they have to say
I think that's fine.
Do you have to be like extra fancy?
I mean, well, here, let me say this. So that's a good question. Kayla asked if you have to be extra fancy. No, don't bust out the thesaurus, to the full extent. But if you can use a chemistry term accurately, oh my gosh, yes, use it, right? Meaning, if you are asked about, I don't know, the strength of a bond or the polarity of a bond, please use the term electronegativity, right? If you know what something is called, what a concept officially is called in the chemistry world, use the actual word. Don't describe it in vagaries, right? Don't describe it as like, well, that one draws electrons more towards itself than the other one. Okay, you just defined electronegativity, so use the word electronegativity. You know what I mean? You can use the vocabulary of the class in your responses, and you should.
Are we allowed to do like the someone?
Totally.
So, like, if we
But
don't remember the French guy's name,
French
that
man.
white French guy's name, we can always
This
just
is
drop
dead red.
Le Chatelier?
well, there's a million of them.
If we get close to it, like if we kind of butcher it, but they like get that we're trying to say with Chatelier, will they give us?
I mean, assuming that's like close enough.
Close
So if we say dead white guy, dead white French guy.
Yeah, don't do that.
No, we can't say that.
Don't do that.
What if I do?
Don't crack jokes on the test.
Like we say,
Well, what-
Le Chalet or something.
The chalet I'm in.
If you don't actually know his name, maybe then don't. I don't know. Okay, so after the change was made at time t1, the partial pressure of SO3 increased while the partial pressure of O2 decreased. Explain this observation. Okay, we had a chemical reaction, right? It wasn't on this slide, but there it is. They're still referencing this reaction from the previous chunk of the problem. So this is what we got going on. I want to bring that back to where I'm at, because that's really what I'm referencing. This is a whole Le Chatelier shifting equilibrium question. So let me bring back that occurrence. Oh, my X moved. Okay.
Close that.
Try this again. Oh, wow, yeah. What in the world?
Must have had that like.
Oh,
Oh, you have like a text thing over. That's what you do. So like you have a picture and then you have text. Other text.
So I want that reaction back. So I have 2SO3. And that's turning into SO2 plus O2, right? Is that all it is? That's right. So let's think about the stress that we just introduced, right? At time t, we added SO2. What did that do? Well, this increased. Which way are we shifting? Towards the reactant side. So, all right, let's talk about why that occurs, right? So we can name drop Le Chatelier if we want to here. Okay. How do I want to say this though? I want to be careful with how I say it.
Did you talk about how like it makes the reaction shift to the reaction?
Yeah. So
That's all.
okay, after the addition of SO2, the reaction would shift towards the reactants. I don't know if I mean, as a result,
Yeah, you still have to add.
yeah, I do, but I think that's like the crux of what they want. Yeah, okay, let me cap it off like this. So I add SO2, it shifts towards the reactant side.
So I'll make more reactions.
I didn't order to repeat.
Yeah, that's what I want to talk about. I want to talk about reestablishing equilibrium. If I get anything more than that, I think that would be complete.
I'm sure you talk about the
What does the answer?
I don't know. I feel like that's enough. The increase of the partial pressure of SO2 perturbed the equilibrium,
Why?
which responded by consuming O2 and producing more SO3 as new equilibrium concentrations were established.
Is perturbed like a chemistry term?
No.
Or is it just a random?
It's like a disturbance, right?
Yeah.
No, it's just a random word. At equilibrium, the reaction quotient K was equal to Q. So additional SO2 increased the partial pressure of SO2, increasing the value of Q such that Q is greater than K. The reaction proceeded in reverse to reestablish equilibrium, consuming O2 and producing more SO3.
Do you really have to say all that?
Yeah, that's fine.
Yeah. All right. So let's get fancier.
Do we have to do Q
How do we know that they want all that?
They don't. That was two options. There was an or in there.
Okay.
Hold it.
Okay.
That's a lot.
Sorry, there was an or in there. I sincerely apologize.
I was like,
Um,
I don't know about Q.
As a result, O2 was consumed. And additional SO3 yeah, was produced. Cool? I think that's fine. Yes. I would write the word because, but yeah. Careful with saying SO2 is going to decrease.
That's what I thought. I just added that up.
Yeah, the reason why I say to be careful is because like it's an initial increase and then a slight decrease, but overall from there to there it's increased in total. So careful with how it gets worded.
So should I like erase that part?
Yeah, honestly, just talk about the O2. You're probably better off that way.
Should I just added it because it does decrease. It just
Correct, after the fact. And the net result though is positive. That's the hard part. All right, E, use the information above to answer the following. Write the expression for the equilibrium constant Kp for this reaction. Okay, sweet. We just want to set up K. That's easy peasy. Kp equals products over reactants. Now, where's the danger? Pressure. They do not want molarity. This is pressure. If you start doing this crap, you are wrong.
RIP.
Yup. This is not molarity.
What
You
if
do
you
not
do like
use
a-
brackets.
What if you do like a square parenthesis? I suppose that'd still be wrong because you don't have the P on.
The partial pressure of SO2 multiplied by the partial pressure of O2 divided by the partial pressure of SO3. Now, we need to raise these to their appropriate coefficients as well, right? So the SO2 was squared and the SO3 was squared. It must be in this format. If you write molarity, you are wrong. It needs to be partial pressure because this is the constant, equilibrium constant using pressures.
Isn't that still wrong though? Because that's an equation, not an expression.
Same thing.
Go talk to 8th grade math teachers about that. They'd be very-
God.
Oh, really?
That should be on you.
No. AP doesn't care about that, I guess. Determine the value of KP.
How would you do that?
Great question.
You
Doesn't
look at the
matter.
graph.
Doesn't matter,
Oh,
yeah.
it doesn't matter.
But yeah, now they didn't give us any numbers, did they?
Well,
We
so-
have to use the graph. Yeah, we have to go back and interpret the data from the graph. And I think we can do okay. I think we're going to be just fine being able to read this thing. So I'm going to use before. I don't know why. I think that feels nicer in my head. 5-0 looks right on it. That's nice. 3-3.
That's what I said.
Sure.
And then,
2.16.
I'm sorry?
0.16.
I'm going to go 1-7.
I assume they have
Because
a
this would be
range,
like
right?
a, this would be like a 1 over or 1 below, right?
Yeah, I guess.
So
I'm
5-0,
kidding.
3-3,
I assume they have a range.
1-7.
For this one, then they would probably have a range of answers.
Yeah. They have both before and after on their answer keys, but I can't imagine they wouldn't accept like. I mean, well, I don't know. I mean, again, it's pretty easy to read.
Yeah.
Just be careful, maybe. I don't know. I think they would accept it either way, but certainly I think we can interpret it pretty accurately.
But like if you use 0.6 instead of 0.7, it would be wrong. 0.16, sorry.
I don't know. I don't think so.
I hope not.
I hope not as well.
Jordan's
That feels overly harsh, right? Because it's especially, again, is the concept to like make sure you read your graph extremely accurate, or is the concept to like understand how to solve for K? It's to understand how to solve for K. So I'm assuming they would be okay. What did we get here?
I got 0.0697.
I got 0.741.
That's what I got too.
0.17.
Here,
Yeah, I just 0.16.
0.074? Yeah.
Yeah.
It's only 266.
Yeah, and so let me talk about sig figs again. I know this has kind of been coming up here and there. If you are confident in the correct number of sig figs, sweet. You can use the correct number of sig figs. If you're not confident, use 3. Okay? And either the reason why I've told you to use 3 all year is because it doesn't matter. They will accept 3. If you wrote 0.0740, or sorry, 0.0741, they're going to accept it. Sounds strange, but so I'll phrase it the way I want you to do it. You know the sig figs, do the right sig figs. If you're not sure, use 3. I think that was a pretty nice free response. Little blend, some old stuff, some current stuff, some equilibrium stuff, but I think that was a very, very approachable problem. So with 1 week left, I will be providing some more review stuff next week for you guys. I mean, I kind of gave you that giant packet yesterday, right? And Lamont and Wes, if you guys need one, you can sneak down. Okay. You can sneak downstairs, or I think I have copies on my card. Never mind. But you want to probably revisit some old content. The highlights being probably Unit 3 more than any other unit. Intermolecular forces is a big deal on the test. Hybridization, Lewis diagrams, molecular geometry stuff is kind of sort of there. Again, a lot of that geometry lends itself to being tetrahedral. Please know that tetrahedral is 109.5. Okay, you're probably going to need that. That's just a memorization thing.
Don't they give you like a range though?
They do, but 109.5 is always going to be within that range. Yeah, if it's a coordination number of 4, they will accept 109.5, regardless of it, even if it's not. Meaning, like,
What if I want to use another?
I wouldn't push your luck too much. Just take this. Oh, don't. Not recommended. So I'll give you a couple other little like tips and tricks and things to know. One thing that consistently shows up too that throws kids for a loop is they like to use organic molecules, meaning they like to use molecules where it's like random carbons and hydrogens and oxygens, and you're like, I have no clue what that is. But organic chemistry, organic molecules, I should say, are always gonna, or almost always gonna follow pretty rigid guidelines. Here's what I mean. And I'll say this again next week because I think this needs to be repeated multiple times this week because it's going to come up and I don't want you to fall into the trap. When you have carbon in a random molecule, carbon's going to make 4 bonds and have no lone pairs. Always. When you have hydrogen in a random molecule, hydrogen's going to make 1 bond, no lone pairs. When you have oxygen in a random molecule, you're going to get 2 bonds, 2 lone pairs. That could be a double bond if there's nothing else on the other side of the oxygen, double bond with 2 lone pairs. Or it could be an oxygen in the middle where there's a bond over here, there's a bond over here, and there's still 2 lone pairs.
Wait a second. You said before that it's sometimes.
What do you mean?
Or it could be 3 lone pairs.
Oxygen?
Yeah.
If it has 3 lone pairs, you got a negative charge. So certain ions will do that. But for any organic molecule they give you, you're going to end up with 2 bonds, 2 lone pairs, because they're going to give you neutral stuff. But if it's a charged particle, your oxygen would have something different, yes. But those are really good rules to understand, because sometimes they make you draw Lewis diagrams with weird organic things. And you're like, it's too big. I don't know how to, we've never did one this big. But the rule of carbon 4 bonds, no lone pairs, oxygen 2 bonds, 2 lone pairs, hydrogen 1 bond, no lone pairs goes a long way. And nitrogen sometimes gets a little trickier, but 9 out of 10 times nitrogen is going to be 3 bonds, 1 lone pair. I'll remind you of that, and I'll make all of you write that down next week somewhere.
Oh, such a nice
No,
conversation.
hold on, we already.
Well, it shows up consistently, and it's kind of an organic thing, but it's an easy thing that I can simply just relay to you guys, and then you guys will get it right. You can hang out for another, I don't know, 15 or so minutes, but our department eats lunch usually at like 11:15, so I'm kicking you out certainly when other people start showing up. But if you have a couple questions, if you've been working on some other stuff and want to get some side things answered, please hang on for a little bit. Otherwise, have a lovely weekend. Thanks for blowing up your Friday morning.
I'm here all day, Mr. Rose, and I have so many questions.
Hey, I don't, okay, fine.
Let me stop on recording real quick.